Hello students, how are you doing? Today we're going to be going over some inverse functions and how they relate to trigonometry. A inverse trig function works exactly the same way as a regular function. It undoes the action of any particular function. So, for instance, if you have, the sine, already have sine on here, so let's say, if you have a cosine acting on an inverse cosine, well, the cosine function undoes the action of the inverse cosine so that you simply equal x. And it goes both ways too. Inverse cosine, the cosine x equals x. Okay, so having said that in our preamble, let's take a look at this guy right there. Note that we've got our x right here, and then we have our y here, right? Y equals sine x. We're familiar with this. We can graph y equals sine of x. We know that will result in a sinusoidal wave. But when we look at the inverse function, look at what happens, right? What was the domain is now the range, and what was the range is now the domain. So, as you may recall, an inverse, for a function to have an inverse, it must be one-to-one. It must pass the horizontal line test. So we're going to have to make some domain restrictions for a lot of these trig functions to work, because if not, they will fail the horizontal line test an infinite number of times. Okay, so applying the domain and range swap will be what is what goes there. So anytime you go from a regular function to an inverse function, the domain and range swap places. A function must be 1 to 1 to have an inverse. If it is not 1 to 1, then we must impose domain restrictions to find the inverse. So what we're going to do here is just graph each of these functions, each of these trig functions, and we're going to look at what would be an appropriate domain restriction in each case. That is impose. Where'd it? Oh, of course it would keep recording. Okay. Alright, so let's go ahead and try and figure out where we can make this one-to-one, where it will pass the horizontal line test. Note that up here at the top, we want to get this as close to the origin or centered at the origin if we want. If we go to the left of the origin, you can definitely clearly see that we will begin failing the horizontal line test. Let's go ahead and just look at a line in there. Alright, so you can as long as it's somewhere in between 0 and 1, we kind of see, anything that we have if we move to the left, we'll begin failing the horizontal line test, as you can clearly see from this blue line we put in there. So let's go ahead and start this off at 0. So that will be the beginning of our domain restriction, and then we'll keep going to the right until we will no longer pass the horizontal line test. And so you come up to here, we're fine. Note that the moment you pass down to, you get past this hump right there, we begin failing the horizontal line test. Shh, Eloise. Like so. Alright, so we have this from here to here, and so note that this implies a domain restriction from 0 over to negative pi. So let's go ahead and put that domain restriction up. So here our domain for the cosine is simply 0 to pi, and note that our range is, as it always was, from negative 1 to 1. And so if I wanted to say, okay, well, what is the domain of the inverse cosine? Well, that would be from -1 to 1. And then the range of the inverse cosine would be from 0 to pi. Right? They're going to switch in every instance because that's the nature of the inverse function as given up here. Okay, so now we're at the sine function. And note that we're still here at the origin. Now we can go to the left without violating the horizontal line test. We go all the way to here. And on the right side, we can keep going until we get up to this hump right there. And so note that if we go any further, we'll begin failing the horizontal line test. Alright, so this is effectively going from -pi/2 to +pi/2. Alright, so again, our domain for sine is -pi/2 to +pi/2. And the range is still -1 to 1. Okay, and so note that the domain of the inverse sine is going to be this. And then the range of the inverse sine will be this right there. Alright, and something I just noticed real fast, we are in 2.5 right now, not 3.6, so make sure you correct that on your handout, although I'll have that correct in the handout that you have, but just note that for the video that's what that needs to be. Alright, so let's move forward. Now we're into secant. We want to know what is an appropriate domain restriction for the secant. Alright, so again, we're not in sine now, we're now looking for the secant function, an appropriate domain restriction. And again, we're trying to get where we have a 1-to-1. Note that if I get that entire, like this piece right here, note I will be failing the 1-to-1 requirement. So we're going to go ahead and impose a domain restriction starting at 0 because we want to get as large of a section as we can while staying inside of as close to the origin as possible. And then I just sweep it over to right there. Now this is an appropriate way to restrict the domain. However, we are looking to make appropriate choices that will be most beneficial for when you get to the calculus. So even though this domain restriction would work, we're going to use a slightly different domain restriction. And the domain restriction we're going to use is going to look like this. So note that we now have two sections of the domain from here to here, and then again from here to here. Alright. Note that we go through all the different values of the secant function, and it is also 1-to-1. So let's go ahead and mark these down. This first section, this goes from 0 to pi/2, and the next section goes from pi to 3pi/2. So once again, we've got the domain of the secant equals, and we're going from 0 to pi/2. Note we are not including the 0. Pi to 3pi/2. Okay, and that is your domain. Alright, and so also note that the range of the secant that starts off at negative infinity comes up to 1, negative 1, union 1 all the way up to infinity. And the domain and range of the inverse will be just the opposite. Alright, now for cosecant it'll be pretty similar. Alright, now we're on cosecant and we're going to go ahead and, again, very similarly, go from, okay, so note that we now have cosecant up. Note that the same domain restrictions we had before still apply, right? We selected in such a way where we have this first part where we go from 0 to pi over 2, and the next part we got from pi to 3 pi over 2. So it's pretty convenient that they both have the same domain. Also note that we maintain our 1-to-1 requirement, and we've gone through all the y values that this function will go through. So let's go ahead and write that in. Alright, so the domain of the cosecant is now going to be the same as the domain of the secant. So 0 to pi over 2. Only this time, I guess we could include that pi over 2 point, and then we go from pi to 3 pi over 2. Alright. Okay. Alright, so now let's go on to tan and cotan. These two will both be pretty similar to each other. So when we run over there, and we are not going to need the second interval, so let's just make that go away. And note that we can get everything with this first little s, we'll go ahead and call that one, and this goes from negative pi over 2 to pi over 2. So a domain for tangent is simply pi over 2 to pi over 2. Okay, now let's look at cotangent. Again, we want to just have that one s in there. So bring that over to here. Bring this guy over here, and note this goes from 0 to pi. And then the range for the tan and cotangent, note that simply is all real numbers, and the range of the cosecant is the same as the range of the secant. Okay, so let's go on. So on this part, we're going to be plotting the inverse function for the following. And so what we got to keep in mind is that the x and y coordinates are interchanged in the inverse function, causing a reflection about the line y equals x. So the two keywords are that the coordinates are interchanged, and this causes a reflection about the line y equals x. Alright, so that's exactly what we're going to attempt to do on this one. And if you are not doing so already, I am very strongly encouraging you to write along with me as I go through these. Alright, so first off, let's get our cosine function down. Alright, so let's go ahead and do the first one. Again, make sure you are doing this on your own and not just blindly copying me, and just kind of double checking your work with what happens here. So first point, it's being reflected about the line y equals x. If you're looking at a reflection in your mirror and you're touching the mirror, the point that you have in common with the mirror is the point where you are touching the mirror. So those two do need to align. Note that this point right here, it's about, just over pi over 2, right? So right past 1.5 is our x value, so that's going to turn into a y value of 1.5, a little more than that, and 0. So we've got another point there. All right, now let's look at this point here, right at pi. Again, remember pi is 3.14, just past the 3, and so that's going to be this coordinate is pi and -1, so we need to now go to negative. You see this -1 here? Well, that's the y coordinate, so it's going to become the x coordinate now. So we got -1, positive pi, so the next point is going to be up here. -1 and pi. Okay, so let's go ahead and put this together. One last point we should look at. Right here, 0, 1, that's going to become 1, 0. So right there. Okay, and so when we graph these, try and, stay as close as we can to the shape, but it should end up looking something like this. Comes through clean and then angles up. And that's it. That's the graph of the inverse cosine function. Okay. All right, now let's look at the graph of the sine. And the graph of the sine, again, we're going to be using basically the same kind of method. Note that we've already cut off or applied our domain restrictions. So sine, the inverse sine is going to go through the origin, as you can see here. And at this point here, we've got pi over 2 and 1, so it's going to become 1 and pi over 2 will be the new coordinate right there. Right, this one got moved over to there. Notice how that is being reflected about the line y equals x. And then this one at negative pi over 2 and -1 will become -1 and negative pi over 2 right here. And again, note the reflection about the line y equals x. And so when we graph it, just try and maintain that reflection there. So we get that. So note that each of these are being reflected about the line y equals x. Please make sure that you are doing this on your own by hand, because that will really help you to make sure that you are learning these graphs better. Okay, now let's look at the secant. We'll be trying to get the inverse secant function. Note that we have a different domain restriction in this one. This is a perfectly valid domain restriction, but it is not the domain restriction that we discussed. The one that we discussed goes from here, or the second part goes from here to there like this. And we disavow this portion right there. Okay, so another thing that we note is that we do have a vertical asymptote right here. And this vertical asymptote is described by the line x equals pi over 2. Now this line is also going to be reflected. It's going to be a line that we can use for the inverse function, only instead of being a vertical asymptote, it is now going to be a horizontal asymptote going through at the same spot right there. And this is described by the line y equals pi over 2. Okay? And so let's start with this guy here. We've got a point here at 0, 1. So now that point's going to become 1, 0. And so we can, go point to point, but just note how this function shoots up along the vertical asymptote. Well, it's going to be reflected, so now it's going to be going along the horizontal asymptote. So this gets reflected in the following way. It will look like this right there. And then the next function, or next part of the function, we're right here. And again, note that this is at pi and -1, so the other point will have to be -1 and pi, which will be about right there. And do note that we have a vertical asymptote right here. And this can be described by the line x x equals 3 pi over 2. So the next line will be y equals 3 pi over 2. And so the tan function goes to the origin 0, 0. That's where it touches the line y equals x. That's where it touches its reflection. And so this is going to be reflected about the line y equals x. We can kind of go off of individual points, or we can kind of go, well, we can kind of see how the reflection looks. So it's going to look something like this. And then this part over here is going to get reflected about, again, this line here. And it'll be something like that. So that would be our inverse tangent function. And note that we do have the asymptotes still in place. Right, here is one of the vertical asymptotes from the original function. And the vertical asymptotes will become horizontal asymptotes here, and then again right there. Okay. So now let's go on. Let's do some actual calculations here. The inverse sine of the sine of 800. Before I say the answer, go ahead and say it out loud. It is going to be 800, right? Because the inverse function simply undoes the action of the function. And also note that if I wrote sine of the inverse sine of 800, the result would be the same. Alright, so next one, a little bit more tough. What you have to remember is that the inverse cosine acts on the x coordinate. Right, on the x coordinate of the unit circle. Whereas the cosine function acts on an angle of the unit circle. Or in this case, we're looking at the sine function that's acting on an angle. So sine of pi over 3, that's the y coordinate when you're at pi over 3. That is going to be square root of 3 over 2. And then you take the inverse cosine of square root of 3 over 2. What angle does it take to get to, an x coordinate of that one? Well, that's going to be pi over 6, because the inverse always outputs an angle on the unit circle. So pi over 6, that's it. Now this is also, note that we're restricting this to be in the first quadrant. We could have not made that restriction, and if we had, then there would have been multiple correct responses. But since we're just keeping this in the first quadrant, that would be the answer. And particularly when you're looking at the graphs of these functions. All right, so sine of the inverse tan of 1. No, we do have domain restriction on the inverse tan. And so the inverse tan of 1, well, that's the spot where the x and y coordinate are equal to each other, right? Because it's going to be the y coordinate divided by the x coordinate. That's when you're halfway between 0 and pi over 2. So we're really taking the sine of pi over 4, which is root 2 over 2. And what I'm talking about, since tan is the x coordinate divided by the y coordinate, this is the one spot where they're the same, and anything divided by itself is going to be 1. Okay, that's it. That's the handout. Hope this was beneficial, and email me if you have any questions.